Hello everyone, today I'm going to give you a presentation about my senior design project, which is called the Robust Readout Circuitry Implementation for Flexible Substrate-based Low-Cost Piezoresistive Biosensor Applications. Firstly, I'm starting with the problem statement, and after that I'm watching this order. And the problem that gives us an idea about to do that project is the silicon-based materials are the main substrate materials for the MEMS devices such a long time because of their outstanding advantages. But the usage of silicon as a sensor substrate doesn't provide properties like the flexibility, disposability, low cost, and ease of fabrication. And as a result of the research that we conducted, we reached the point that the other materials rather than silicon can be used as a sensor substrate and also provide us properties like flexibility, low cost, ease of fabrication, and so on. And as a result of that, we decided to use substrate materials like FR4, polyamide, and paper in our project. You see the piezoresistive sensor configuration in figure 1. We decided to use a Wheatstone bridge circuit in our project as a readout circuit because of their advantages like eliminating the temperature effect through the resistors. And you can see the Wheatstone bridge circuit schematic with one variable resistor in figure 2. From the further point, we decided to add an instrumental amplifier to our readout circuit because the instrumental amplifiers have high common mode rejection ratio, and different than the differential amplifiers, instrumental amplifiers doesn't have any feedback loop. We set the gain by using only the gain resistor, which is called the RG. And after that, we decided to use the multivariable Wheatstone bridge circuit because of their advantages like providing us more sensitive results at the output of the readout circuit. And you can see the related equations in equation 2, 3, and 4 respectively. And the conceptual drawing of the piezoresistive sensor given in figure 5. In the time that we worked on the piezoresistive layer, we considered 3 main points, and these are the width of the piezoresistive lines, the proximity value of the piezoresistive lines, and the number of fingers. And the fabricated and perforated piezoresistive sensor image is given in figure 6. And for the proposed readout systems, we proposed 3 different readout systems based on the FR4, polyamide, and paper substrates. And we decided to use the paper-based readout system in the future. And we concluded the project with the usage of the FR4-based and the polyamide-based readout systems. And you can see the calibration plot of the both paper-based and the polyamide-based sensors in figure 8 and figure 9 respectively. And these plots are showing the normalized voltage change depending on the applied weight to the sensor. And by looking at the slope of these plots, we obtained the sensitivity values of the paper-based and polyamide-based sensors. And the sensitivity value of the paper-based sensor calculated as the 0.038 millivolts over milligram, and the sensitivity value of the polyamide-based sensor is calculating as the 0.073 millivolts over milligram. And for the conclusion, the readout circuits, including Wheatstone bridge circuit and the instrumental amplifier, were designed, fabricated, implemented, and tested in this project for paper and polyamide-based piezoresistive sensors. And for the future, we want to find an application area for proposed readout systems, and we want to return to work on all paper-based sensor system. And that's the end of my presentation. Thank you for your attention.